Hello everyone and welcome back to this next lecture in the machine simulation series. And this is where we had left off last week, where we had written this equation for the law of conservation of energy. So basically we had said that since an induction motor is an electromechanical device or machine, we can apply the law of conservation of energy in this particular manner. That is, we can say that the electrical energy which is input to the motor results in mechanical energy which is produced, because after all that is the major output that we are interested in. This is a motor and it has to move, so that movement is going to result in mechanical energy. There is, besides that, energy stored in the magnetic field. This energy stored in the magnetic field is due to the fact that the motor is an electromechanical machine and the magnetic field is fundamental to its operation. And when you have any magnetic field, you always have energy stored in it. Besides that, there are electrical losses, which are basically ohmic losses, because after all you have stator windings which have a resistance, you have rotor bars which have a resistance, and when current flows through any of them, they will produce ohmic losses. So these are electrical losses. The mechanical losses are mainly, you could say, frictional losses. There could be also some other forms of losses, maybe not exactly friction due to vibration, but these mechanical losses are also there. And the last are, of course, magnetic losses. Magnetic losses are the losses which are there in the magnetic field. These are, you could say, hysteresis losses, eddy current losses. And there may be a few others which might be a little complicated for us to model. But these are the main forms of magnetic losses. So this equation seems to now account for almost every type of, at least, or every major component of energy which is being involved in this induction motor. What is input, what is output, and what other forms of energy which are being absorbed of the motor, either in the magnetic field or as losses or as mechanical losses or as magnetic losses, right? So now that we've arrived at this equation, or rather this relation, because it's not really an equation yet, now that we've arrived at this relation, we now have to somehow write an equation such that we can now express parts of the equation as analogous to this particular relation, so that we can start writing or at least deriving the different components of this equation. Because after all, that's what we are interested in. We are interested in equations for the mechanical energy, for the energy stored in the magnetic field, and so on and so forth. So, as before, if you are interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses which you can find on my own website, which is pythonpowerelectronics.com. So this website, that is pythonpowerelectronics.com, is the home page of this project, where you can find almost every material related to this project, may it be books, may it be video lectures, or may it be actual full-length courses. So I would like to show you some of the courses which you can find by clicking on this button, Learn. So if you click on this button, Learn, you arrive at the link for the, or rather the page for the courses. I have as of now 5 courses which are available on different platforms. So very first course is called Simulating Power Electronic Circuits using Python, and in this I talk about the basics of how you can use Python and Python Power Electronics to simulate basic power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and packages such as the SciPy package and the signal package within SciPy to analyze and design filters for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to model magnetic components such as inductors, coupled inductors, and transformers. The fourth course I have is called Control Analysis with Python for Current-Connected Converters, and in this I talk about how you can use Python and packages such as the Python Control package to analyze and design controllers for power engineering applications using the example of a single-phase inverter connected to a single-phase grid. And the very last course I have is called Why Specialize in Power Electronics, and this is a free course which is targeted towards either junior undergraduate students or even high school students who have not yet chosen their domain of specialization. And this course aims to talk about some of the challenges and opportunities available in power electronics. So all these courses are available on 2 platforms, which is Decibels Labs and Udemy, and you can click on any of these to go to the link for the course. The link for this page is provided in the description of this video. If you're interested, please do check it out. So with this, let me return back to my lecture. So this is where I was. Now, as I already said, we have created this relation of input energy is equal to output energy plus energy stored and energy lost. And we further broke up all these different components. So now let us try to write some equations with which we can arrive at this relation, or at least we can extract parts of this equation, because essentially what we want are expressions for the different components of energy. So now writing such an equation is actually not very straightforward, and that's one of the reasons why I would like to take a little bit of time to come upon how this equation can be written, right? Because usually in most books, in most textbooks, in almost everywhere, they will just write you the final equation, right? They will just say that this is the equation for torque, but it doesn't tell you much, because unless you really go through the process of how energy itself behaves, right, and how electrical systems behave in a certain way, and how we can sort of conceptualize the different forms of energy which are there in an electrical system, it's actually very difficult to just assume that this is the particular value of equation for torque. So let me think of an equation. The simplest equation is, let us try to think of an induction motor. Alright, so let's go back to our browser where I have this induction motor which I've always been using so far. So this is a simple, or rather you can say breakup of an induction motor. This is a squirrel cage induction motor and it's single phase. So you can see here, this is the expression. So here this voltage V is the input applied voltage, right? So typically if you have something like, for example, you have a stator, you might have some terminal somewhere here, could be anywhere, could be here, wherever. And you usually connect your input voltage there, right? So that means you're connecting a single phase input voltage at some terminal in this stator, right? That could be either 120 volts 60 Hertz or 240 volts 50 Hertz, wherever you live in the world. Now, besides that, you see there are two windings. Again, forget about the second winding because we haven't talked about it yet. The need for the second winding will come later. For now, just assume that we have one single main winding, right? So this connection here goes into energizing the stator winding, which is this inductance L1, right? That represents the inductance of the stator, self-inductance of the stator. And here there is the squirrel cage rotor, right? So that's just representing, it's not really connected. You can write, we've already done it. You can express the equivalent circuit of an induction motor, and we've done that as well. So for example, if you go all the way back, we have written the equivalent circuit of the induction motor, right? So you can also think about this. Now, let's suppose we forget about all these things, right? We forget about the auxiliary winding, right? Why is the auxiliary winding needed? Because a single phase induction motor is not self-starting. And I will talk about this later. For now, forget about it. Let's also forget that this squirrel cage rotor exists, right? So let's just look at this induction motor as a simple inductance, right? So let's go back here to our sheet and let's do that. So let me just quickly draw the circuit. What's wrong with my mouse? Yeah. And let me quickly create this. So now I'm going to just join this, and here I will delete it and I will say input voltage, right? Or actually let me use the Python power electronics schematics. I'll just say voltage V in, and here let me delete this. I will just say inductance, inductor L. I'll say LS because this is the self-inductance of the stator. I will say delete this. I will say resistor RS, right? For now, do not worry about how these are linked to here, right? We are representing the induction motor as a simple inductor with a parasitic resistance. That's all that is, right? So if you come back here and have a look, all we are saying is we are going to cut out this entire part of the circuit. So just forget that this everything right of this does not exist. All we have is this voltage feeding this inductor. Now they haven't shown a resistor, but quite obviously a winding will have a resistance, and that's all we are saying is we are putting a certain parasitic resistance in series. So let's come over here again. So if we have this equation, or rather we have the circuit, we can very simply write an equation for this. So let's call this V, let's call it V, right? V is equal to L Ls di by dt plus Rs into I, right? Okay. Oh my god. Okay, it just doesn't like this. I don't know how to deal. Yeah, okay. So this is the equation for our induction motor, assuming for now that it's just an inductor. So V is equal to L di by dt plus Rs into I, right? Now here there is a little bit of confusion that we have introduced, or rather we have assumed something. We are assuming here that this Ls is a constant, right? Now for an induction motor, we have already seen before that inductance need not be a constant, right? We've already seen this in some of our previous, all our schematics. We've seen that in many types, like for example, when you come all the way here, when you come all the way here, we have seen that there are some which are not constant, but rather dependent on the angle. Now, for a single phase induction motor, and particularly for a squirrel cage cylindrical rotor, we have said that the resistance and the self-inductance are independent of the rotor angle, but the mutual inductance is dependent on the rotor angle. Now, for now, we are not talking about self and mutual inductances. We are just representing the entire motor as an inductance. So therefore, really speaking, in this simplified equation, we are bringing in both types of inductance, right? So let us for now assume that this self-inductance here is not just a self-inductance, right? So let me just delete this Ls because it becomes a little misleading, because it feels like as if we are only talking about the stator, but we are representing the entire induction motor. So let me just get rid of this Ls and this Rs, and here we have L. Okay, we are assuming this L to be a constant. But if we say that this L represents an induction motor, then it's not really constant, and we've seen this, right? If you want to know how we came upon all this, just go back to some of the previous lectures. We drew several flux diagrams, and we came upon this conclusion about why some inductances are independent of the rotor angle and why some are dependent on the rotor angle, right? Go back and have a look at those lectures. But for now, if we have an induction motor, we have to loosen this assumption. That means this assumption is incorrect. So which means we have to rewrite this equation. So how do we rewrite this equation? We just come back here. We say d into Li divided by dt plus Ri. Okay, no, I don't like this, the way it changes it to capital, because it messes my equation up. Yeah, okay. So we have now said, we've taken this L into it, because remember, in differentiation, you can remove the constant, if you can remove any factor if it is a constant. Now we are saying that L may not be a constant. The reason, because this entire L, this inductance, represents the inductance of the induction motor. So this equation, as we all know, right, Li, L into I is equal to psi, which is the flux linkages of the induction motor. You can say of the stator, but for now we just say of the motor, because we are representing the entire induction motor as just one inductance, right? Just for the sake, this entire description is for the sake of starting to write some equations so that we can figure out what's happening, right? So we have now come to this equation. Now the question now arises, what if I take this equation and try to convert it more into a power equation, right? So how do I do that? Let's say I multiply both sides by the current I, and there's nothing wrong with that because you can always multiply both sides of any equation by any variable or any constant. It's not a problem. So I can say V into I is equal to I, come on man, probably you'll have to use some kind of specialized equation writing software, but anyway, I'm too lazy for that. Ri square. So this equation now, I have multiplied both sides by I, right? So there is now on the left hand side V into I, and quite obviously we all know V into I is just power, right? And in this case we can say it is input power, because this voltage is the voltage applied across the induction motor and the current which is being drawn is the current drawn by the motor. So quite obviously the product of this voltage and this current is the input power to the induction motor. Now what about all this? Let's think about this a little later and let's come and jump on this. We have here Ri squared, and this we all know very well to be the ohmic loss. These are the ohmic losses in the induction motor, right? So we now have an equation for, we are saying that this equation here is an equation that relates input power, losses, and some unknown quantity here, right? This unknown quantity, let me write it here, is the unknown quantity and let me see if I can remove this I. Yes. Oh, come on. Okay. So this I dLi by dt is the unknown quantity, and this quantity here is what we need to sort of figure out what it is. Now, if you go back and have a look, it's very clear that we are coming somewhere close to what we were trying to do, right? That is input energy. Of course, we are talking about energy here, and here we're talking about power. So there are two different equations, right? These aren't exactly comparable. This is energy, this is power, right? Power is the rate of change of energy. So, but still, you can see here, we are slowly coming towards some kind of analogy. That is, input power is equal to losses plus some unknown quantity here. And if you look, it appears like as if this unknown quantity here is beginning to represent something here. This mechanical energy and energy stored in the magnetic field. We can't relate it directly. The reason, this is energy, this is power. But you can see the analogy already coming. Now the only question that arises is, here we are talking about ohmic losses. But here there are all these losses here, electrical losses, mechanical losses, magnetic losses. What do we do with all that? The question is, when you are modeling, now if you are trying to model an induction motor, we have to sort of make some kind of assumptions. Now, unless you're looking at a very, very detailed induction motor, extremely, like you want to model mechanical losses exactly, you want to model the vibration exactly, you want to know exactly how much hysteresis and eddy current losses are there. Unless you're going into that much detail, you don't really need to know exactly what are the kind of losses you have. In many cases, it is possible that we can represent this resistance here, right? And we can also choose stator and rotor resistances in such a way that they also kind of bring in the mechanical and magnetic losses to some extent, right? It is possible. So therefore, it also appears like as if this last part of the equation can be accounted by these ohmic losses, that is I squared R, right? So With this, I'm going to stop this lecture now because I would like to take some time over it, and I would like to also let you guys, if you're watching, whoever's watching this video, to try to figure out how we are slowly moving from this law of energy conservation and from a simplified circuit of an induction motor without all those details, right? Without any of the details that we have here. Very simplified equation. And the only reason we're doing this is so that we can slowly start quantifying the different components of energy and power. Now, where are we going with this? We slowly have to now create this energy equation from this power equation, and with that we have to actually figure out what is this energy stored and the mechanical energy that results. That's where we are going towards, right? So slowly and gradually we will get there. So if you have any doubts about what I said in this lecture, please do either comment or send me a message or send me an email, whichever is your preference. Otherwise, next week I will continue and we will slowly start writing the energy equation and start trying to link these two. So, thank you so much for watching and see you soon. Goodbye for now.